Hello everybody, Earth.Otherwise here to continue our journey through game programming in C++, start to finish by Eric Yazwa. We are going to need to be able to load model data into our game. We can try to program this manually, but quite frankly there are so many different modeling programs and they all have different model data that making a model loader that isn't garbage would take far too long. So we're just going to use Open Asset Importer Library. It can be downloaded in the first link below. This is all review, but say it with me now. Download the latest release, set up the folder either with the setup or unzipping, run cmake, get the include folders, put them in the include folder of our own, grab the library files. This includes the .exp and .ilk files as well as the .pdb ones. I'm not sure if they're necessary, but we can do testing later if we find we need it. Pop them into our library folder and then grab all those .dlls and you know where they go. One thing I forgot to mention, you may need to pop open that solution and run the release and debug builds of the code in order to get those folders. Always remember to add the new library files to the project properties, and we're ready to start. Next, we create a file I called oasimp. Here we include asimp's importer.hpp, scene.h, and postprocess.h. In the engine's namespace, there will be only a single function. Void returning load asimp, which takes a char star file path, a reference to a vector of unsigned shorts called indices, a reference to a vector of glm vec3s called vertices, a reference to a vector of glm vec2s for UVs, and a reference to a vector of glm vec3s for normals. Basically, you give this function references to the vectors you want the data stored, and it will fill those vectors for you. Now the definition of that function. Make an asimp importer, fill a const AI scene pointer using importer, read file using the importer's read file, passing in our file path, and setting any flags that we want to use. In this case, we're going to use AI process underscore join identical vertices and AI process underscore triangulate. If the scene isn't filled, then throw an error saying that we couldn't read the file. Asset importer can give us an error string as well. From this point, all of our variables will come from the first mesh in scene's mmeshes variable. For now, we're only worrying about the first mesh because we're currently working with simple meshes. In more advanced meshes, there can be multiple meshes in a single object. Like a person might have a separate mesh for their arms, legs, and torso and head. So moving on, we reserve data in each of our vectors. All but indices, we reserve an amount equal to the number of vertices in the mesh. With indices, we reserve equal to the number of faces multiplied by 3. Now, for a number of iterations less than there are vertices, we do the following. Push back a vertex by filling a glm vec3 with m vertices.x, y, and z. Push back a pair of UVs, or the UV, by filling a glm vec2 with m texture coords 0, I, .x and y. Push back a normal by filling a glm vec3 with normals x, y, and z, and push back 3 indices with m faces I.m indices 0, 1, and 2. In there, we mentioned flags for reading a model file. Obviously, these flags change how the data from a model is stored. Without some of the flags, we can actually render models the way we were before. However, since we indicated that we wanted identical vertices fused, that means that our data footprint will be smaller, especially for larger meshes, and we will also need to render in a new way. Instead of just going through the list of vertices and drawing a triangle for every 3 vertices in the list, we instead are using indexing, which points to 3 vertices in the list, and we draw a triangle based on those 3 vertices. The advantage here is that we can point to the same vertex multiple times instead of having multiple copies of that vertex for every triangle we want to draw. Something important to note, we're using multiple buffers for vertex, UV, and normal data. However, each of these buffers is the same size. You might be wondering why that is if we only need 1 copy of each variable. For example, in a cube you might have only 2 UV coordinates because yours is a repeating pattern that just goes from the top left to the bottom right of the image. However, because you have 24 normals, 3 for each corner, which you need to do the lighting properly, then you also need 24 UV coordinates. This is because OpenGL only has one index buffer, and that index buffer only stores one value for each index. This means that if we want to draw vertex 20, then there needs to be a position 20 in each of our buffers holding the correct data for that vertex. So you might be asking what indexing actually does. Well, you are aware that each face of a cube is made up of 2 triangles. Along the edge that those 2 triangles share are 4 vertices. They share the same position, they share the same UV coordinates, and they share the same normals. They are truly identical. Indexing allows us to use 1 vertex here, or 2, instead of 2, or the original 4. For a cube, or something else that has a lot of edges that needs to be lit differently, the benefit of indexing is lessened. But if you were to have, say, a sphere, then you would have a vertex that is referenced many times, an increasing number of times as your sphere increases in definition and smoothness. So now that you can understand why we are using indexes, let's actually do it. A new class called OMeshRenderer is required. Include vector and glm/glm.hpp. Along with it, there will be OMesh. OMesh will be a struct that contains vectors for indices, vertices, UVs, and normals, as well as a GLUint for a texture ID. OMeshRenderer will have a void returning init function, followed by a void returning addMesh function that takes a GLUint texture ID and a char pointer to a file path. Then we have a prepareMesh and renderMesh function. Private variables include a GLUint mVertex buffer, mUV buffer, mNormals buffer, mVAO, mIndex buffer, and a vector of OMeshes. All the GLUints should be initialized to 0. Now into the .cpp file. Include oasimp and gl/glue.h. The mesh renderer will be a lot like our multisprite. We'll need to make a vertex array object and bind it. Then we generate our vertex, UV, normal, and index buffers. Now we enable 3 vertex attribute arrays. In the first position, we bind the vertex buffer. Its GL vertex attrib pointer goes to attribute 0, has a size of 3, is a float, isn't normalized, and has a stride of 0, and has an offset of 0 cast to a void pointer. In the second position, that's vertex attribute array 1, because we start at 0. We bind the UV buffer. Its attrib 1, as I said, has a size of 2, is of type float, isn't normalized, has a stride of 0, and a 0 offset. Third position is the normal buffer. Everything else is the same. 3 is the size, of course. Finally, we bind 0 for the vertex array so that we don't accidentally make changes to it. addMesh will make a new OMesh and then pass its variables into loadasimp function with the file path that was added to the addMesh. Then we set the texture of the mesh and push it back onto our mmesh's vector. PrepareMesh is a lot like our prepareBatches function. First, bind the vertex buffer, then using GL buffer data, we fill the array buffer with the vertex data of the first mesh, just the first mesh right now, as I said. We do that by multiplying the size of the vertex buffer of the first mesh by the size of a glmvec3. Then we give it a reference to the first element of that vertex buffer. Right now, we're just going to do a GL static draw. Follow this up with doing the same thing with our UV, normal, and index buffers. The main difference is that the index buffer is an element array rather than just an array buffer. Finish the prepareMesh functions by binding 0 to the array buffer, element array buffer, and vertex array buffer. Now we render. First bind our vertex array object, then bind our texture. Now draw our mesh using GL draw elements. We are drawing triangles. We are drawing the number of vertices equal to the first mesh's indices.size. Then they are of type unsigned short, and an offset is a cast to a void star of 0. Finish that off by binding the default empty buffers for our element array buffer, and vertex array object. Now we're going to make our new shader. Really, it's exactly like our current shaders, except we're not sending a color in. So copy the shaders, I call them mesh shaders, then go in and remove the incoming and outgoing color from the vertex shader. In the fragment shader, remove references to the incoming color. We just have to remember that down at the bottom of our fragment shader, where we use color.w, we need to set that to 1 because that's the transparency of the pixel. Now we find ourselves in our GUI.cpp. Here, where we enable GL blend, we have to also enable GL depth test. We need to do this because while the depth test is non-conductive to rendering our GUI properly, we need it functioning properly when we are drawing things in our main game loop, which we won't be if the depth test isn't enabled. Now into main.cpp. Include omeshrenderer first, then we need a whole new shader program ID because we're using a new shader. Compile and link that shader, then we need copies of all our IDs for perspective, camera, etc. But finding the uniform locations in our new shader program rather than the old one. Now down in our main game loop, we're going to initialize our mesh renderer and add a new mesh. I'm using Suzanne, which is a testing mesh used by Blender and can be found in the second link below. I put the mesh in a meshes folder. I'm going to make it green because we always have that loaded up. Now we'll need to copy our uniforms in our while loop too so that our meshes render correctly. Just make sure they go to the correct IDs. Then we simply call render mesh and that should be it. Make sure your camera is close to 000 though, because that's where your mesh is going to be rendered. At this point, if we were to attempt to push multiple meshes on the screen, either the same one copied or different ones, we would only succeed in clustering several meshes into the 000 position. Now we look back into OASIMP because I made a mistake. When we fill our indices, we aren't doing that once for every vertex. We're doing it once for every index, obviously, and that number can be found in mnum faces of our mesh. So quickly put that in a different loop. Now our mesh should be easily viewable. I've used a striped PNG image instead of green so that I can better see the definition of the mesh and see if there are any bugs. But anyways, that's all. I'll see you in the next one. Here are some additional corrections to a couple of mistakes that I made in the video.